So we have to comment on the correct structure of P and Q. We had already seen before that the compound P was benzaldehyde and the compound Q was benzoin. So benzaldehyde and benzoin are correctly represented in the option C. So we have to mark option C as the correct answer to our question. Let us look at the next paragraph for question number 33 to 35. Any substance that rotates the plane of polarized light is said to be optically active. If a pure compound is optically active, the molecule is non-superimposable on its mirror image. And if a molecule is superimposable on its mirror image, the compound does not rotate the plane of polarized light and is optically inactive. The property of non-superimposability of an object on its mirror image is called as chirality. So let us look at question 33 now. Among the following, the optically active compounds are. So students, in the first option, we have aspirine. So the planes of the atoms or the groups are already represented to us. So we can see that these NH2 and this H lie outside the plane of this paper, whereas these NH2 and this H lie on the plane of the paper. So if we try and find a plane of symmetry in this structure, will not have any plane of symmetry, as these groups are different to each other and these groups are also different to each other. If any of these circled or the hash groups were identical, then we would have gotten a plane of symmetry in this structure. So this is optically active. Yes. The same is the case with the second option, in which the methyl group and the hydrogen group are not in the plane of paper, while the other atoms are all in the plane of paper. So again, if there were to be a plane of symmetry in this molecule, the circled groups or the hash groups should have been identical to each other, either one of those. There is no point trying to find a sigma about this because the planes of these hashed and the circle atoms are different in both the cases. So this is also optically active. Looking at the third option, so in the third option we have a meso compound. If we try and draw a plane passing through these group, we'll have a superimposable mirror images of each other. So this is optically inactive. It has a plane of symmetry. And if you look at the fourth option is also chiral. It also does not have a plane of symmetry. So the optically active compounds among these four species are options A, B and D. So we have to mark option A, option B and option D as the correct answer to our question. Let us look at question number 34 now. How many compounds have optical isomer less than 2 to the power n, where n is the number of chiral centers? So students, if you look at these structures A, B, C and D, let us first try and find out the chiral centers. So it has 2 chiral centers. The second structure also has 2 chiral centers. The third structure also has 2 chiral centers. So we know about bridgehead compounds. The bridgehead compounds can have only a cis configuration here. So if this structure takes a trans form, the molecule will be very highly strained. So students, this compound can exist only in this cis form, and it is going to have only 2 stereoisomers, while the other one will be an enantiomer of this structure. So it has a total of 2 stereoisomers. It does not have 4. So this satisfies the condition given in the question. If you look at this structure, it also has 2 chiral centers, but it has a possibility of a meso compound. So it will have a cis and a trans form. If we look at the cis structure, the cis is going to be optically inactive, as there will be a sigma, whereas the trans form will be active. So it is going to have only 3 stereoisomers. So this also satisfies the condition given in the question. Similar is the case with the structure given in option C. It is similar to the option A. It is also going to have only 2 stereoisomers. This also satisfies the condition given in the question. And if you look at the fourth option, there is still again a possibility of a meso, where if any 2 of the OH groups are cis to each other, there will be a sigma which contains the third OH group. So this is also going to have less than 8 stereoisomers, as there is a possibility of meso formation. So we have to mark options A, B, C and D as the correct answer to our question. Let us look at the next question. Question number 35. We have to select the correct statements. So option A, enantiomers react at different rates with other chiral compounds. This statement is correct, students. The enantiomers On reaction with other chiral compounds, they form diastereomers. And during the formation of these diastereomers, the transition states which are formed are different. So this statement is correct. Let us look at option B now. The presence of optical activity always proves that a given compound is chiral, but its absence does not prove that the compound is achiral. This statement is correct, students. If the compound is chiral, then the compound will be optically active. Yes. And if you look at the second part, its absence does not prove that the compound is achiral. So students, when we have an equimolar mixture of two enantiomers, both these enantiomers will be optically active, but when they are present in an equimolar amount, they are going to cancel out each other's rotation of the plane polarized light. So in that case, the optical activity will not be observed, but it does not imply that the compound is achiral. So this statement is also correct, students. Let us look at option C now. For 1, 2, 3, 4, 5, 6 hexachlorocyclohexane, there exists 7 meso compounds and an enantiomeric pair. Students, let's try and draw the stereoisomers of 1, 2, 3, 4, 5, 6 hexachlorocyclohexane. So we can have all the chlorine atoms coming out of the paper towards us. So this is a meso compound. It has a plane of symmetry passing through any two Cls. So it is going to have a sigma. Then we can have one chlorine atom going away from us while the others are still towards us. So this is also meso. We can have two chlorine atoms going away from us. This is also a meso compound. It has a plane of symmetry like this. So in case of two chlorine atoms going away from us, this was a 1, 2. We can have a 1, 3. We can have a 1, 4 as well. So this was the 1, 3. This is the 1, 4. So 1, 5 will now again be identical to 1, 3. So there's no point drawing that. So students, both of these compounds are again meso. We can have plane of symmetry passing through here. We can have plane of symmetry passing through here. These had plane of symmetries as well. So let us now try and draw structures in which there are 3 chlorine atoms going away from us inside the plane of paper. So we can have 1, 2, 3. We can have 1, 2, 4. We can have 1, 3, 4, which will be again the same as 1, 2, 4. And then we can have 1, 3, 5. So if we try and look for plane of symmetry in these structures, we'll have a plane of symmetry in the first one, which was the 1, 2, 3. This was the 1, 2, 4. This was 1, 3, 4, and this is 1, 3, and 5. So this compound was meso. If you look at this structure, this does not have a plane of symmetry or a center of symmetry. This is optically active. And the 1, 3, 4, which we had already seen before, we could have also numbered it as 1, 2, and 4. So both these structures, we can see that they are mirror images of each other. So we can probably place a mirror around here. And if you look at the last one also is optically inactive. It is a meso compound. It has a plane of symmetry passing through this. So this is also meso. So we have 9 different structures, out of which 7 different structures are meso compounds, which are optically inactive, and we have an enantiomeric pair, which is 1, 2, 4 or 1, 3, 4. So the statement given in option C is also correct. We have 7 meso compounds and we have 1 enantiomeric pair. Now looking at the D option now, for 1, 2, 3 cyclohexane triol, there exist 2 meso compounds and an enantiomeric pair. So we have 1, 2, 3 cyclohexane triol. We can draw the structures. We can have all 3 OHs coming towards us. We can have one of the OH going away from us. Or we can have the last OH going away from us. Now, if you look at these structures, we can see that the first compound has a plane of symmetry. It is a meso compound. The second structure does not have a plane of symmetry. It is optically active. The third also has a plane of symmetry. It is a meso compound as well. And the fourth structure also does not have a plane of symmetry or a center of symmetry. So it is optically active as well. Now, as far as these 2 species are concerned, we can see that this structure 2 and structure 4 are mirror images to each other. Okay. So 2 and 4 form an enantiomeric pair, whereas structures 1 and structures 3 are meso compounds. So students, the statement given in option D is also correct. So we can see that all 4 of these statements are correct. We have to mark options A, B, C and D as the correct answer to our question. Let us look at the next section.